I welcome you all for this NPTEL lecture on earthquake resistant design of foundation. And today we are going to discuss 26th lecture, and we are continuing the third module of this course, that is on pile foundation, which is the biggest module in this course. With the pile foundation, we was discussing the piles passing through the liquefiable soils, and today also we are continuing with that. That is the second lecture on piles passing through the on liquefiable soils. So you could see the slides here, and in the slide, as I mentioned, that this is the second lecture on piles in liquefiable soil. Now what we have here, so third module and pile foundations. Within the pile foundations, we have discussed so many topics, and this is the last topic, design of piles in liquefiable soils, and second part of this. Before I go ahead, let me acknowledge, as was the earlier lecture, most of the contents of this lecture also following literature, which is a book entitled as the Design of Pile Foundation and Liquefiable Soils, published by Imperial College Press and authored by Maheshwari et al. The speaker is grateful to these authors to provide this material, and their contribution is gratefully acknowledged, and this is only for this lecture, not for anyone. Now coming to the second lecture on liquefiable soils, what we are going to talk today is first is we are going to discuss inertial loading, then kinematic loading, then kinematic loading in laterally spreading soil, then limit equilibrium analysis in laterally spreading soils, and limit equilibrium analysis with non-liquefied crust. And when we discuss this with non-liquefied crust, two cases will be discussed. One is stiff clay as a non-liquefiable layer. Another is dense sand as a non-liquefiable layer on the top. So let's discuss first one, inertial loading, before we come to kinematic loading. When we talk about inertial loading, you could see the figure 2.1, where a pile group is there, and it is passing through a soft soil, which is underlain by a stiff soil. Pile tips are resting on in the stiff soil, and there are two cases. One case is where pile cap rotation is not allowed. The second case where pile cap rotation is allowed. So both the cases we are going to discuss. What is the effect of inertial interaction between piles and soils? So here, the loading requirement imposed by seismic events on piles requires different geotechnical and structural design of these elements compared with the design of piles under static loading. So compared to static loading, inertial loads which are absent in case of static loading need to consider dynamic loading. Now considering the case of pile foundation on level ground, which is shown in this figure, there is no slope, which comprise of a soft horizontal soil layer in which no soil liquefaction occurs and overlying a steep horizontal soil layer, and the pile foundation passes through the soft layer and rests on a steep layer as shown as we already discussed. But one thing is important to note here, that this soft soil is horizontal, that is not sloping, number one. And so that means we are not considering lateral spreading here. At the same time, the soft soil itself is a non-liquefiable. So here we are not considering liquefaction, but for how the effect of inertial interaction piles and soils when we are not considering liquefaction, that is going. And that discussion is based on two cases. The first case, when pile cap is prevented from rotation, not allowed. So this is pile cap rotation not allowed. The second case, when pile cap rotation allowed. Okay. So let's discuss when it is not allowed. Here, the earthquake motion can be transmitted first of all from soil stratum into a softer layer, and this motion can be amplified as it propagates to the softer layer and finally transfer piles and the super. And this kind of transmission will set cell vibration in the structure, imposing inertial loading on the pile cap. What you have here, the earthquake motion is come from down, it passes through the steep soil, and then finally soft soil will amplify it, and ultimately they reach to the near pile heads and pile cap. And this will set tone for inertial loading. Now this inertial load has to be carried by the piles. If the inertial load is large, then piles can suffer significant lateral displacement. And depending on the stiffness of the superstructure and the pile cap's bearing capacity, pile cap can be either be prevented from suffering any rotation or some rotation can occur. If the pile cap rotations are prevented, then the piles will undergo what is called elastic bending, and in extreme cases, plastic hinges can be formed. The pile or pile cap interface is indicated in figure 2.2. So this is the case when you are preventing the pile cap from rotation. There will be hinges will be formed, and the pile cap will undergo here. Okay. Now the second case, on another hand, the pile cap can undergo some rotation, then the piles will suffer elastic bending, but the pattern of bending is opposite to the previous case. So you see, pattern, first of all, bending is higher compared to the first case, and pattern is also different, which is opposite to the difference that here rotation. Now, in this case, the pile cap can undergo some rotation, then piles will suffer. These types of behavior will be dominated by the stiffness of shallow soil layers. The lateral inertial load on the piles will only displace the soil. When you apply lateral inertial loads, pile cap or pile head, then it will displace the soil in shallow region near the pile cap. If the shallow layers in these regions are soft, then this can be accomplished. On the other hand, if the shallow layers below the pile cap come stiffer or competent soil, then the lateral displacements of piles and the rotating piles cap will be smaller. The piles may attract large inertial loads, the mobilization of the passive soil. Hence, initial loading on the pile is a dynamic load. Peak magnitude depend on the dynamic characteristics of the piles. In particular, the inertial load will depend on the stiffness of the pile relative to that of surface. Naturally, what is the stiffness compared to pile or vice versa? On that, now coming to the next part, this is kinematic load. Here also we are considering a pile group, and which is on the top of their pile group, there is a what is called pile cap is there. And in this case, we have kinematic loading. So earthquake loading differs from other form of environmental machinery induced cyclic loading. This is normal case. How it differs? Because the in-ground motion produces pile loadings in addition to the pile loadings which is derived from the motion of the supported structure. And the in-ground motion generates kinematic interaction between the piles and the soil. As the soft soil layer undergoes vibration due to the arrival of cyclic shear stresses from the stiffer layer below, it will vibrate in the first mode with a natural frequency Fn, which is given by this relation in equation number 1. In this equation, Vs is shear velocity of the soft soil layer and H is the thickness. And it is assumed that this layer is fixed at the base while determining this natural frequency. Now, as was the case for inertial loading, for kinematic loading also we are considering two cases. One case when pile cap is prevented from rotation first, and another case when pile cap rotation is allowed. So here you could see that behavior of the piles are similar what we have discussed seen in case of inertial loading, and there is a formation of the hinges near the pile cap. So continue with this. So what you have this motion which is due to kinematic loading is indicated as a free field soil displacement in figure 2.2. The piles that are located in such a soil layer are forced to follow the motion imposed by the soil. If the piles are relatively flexible, then they will undergo deformations as shown in figure 2.2. On the other hand, if the piles are relatively stiff, then in that case deformations they undergoes will be smaller. So in case if it is stiff piles, then it will be smaller deformation. In case of flexible, then it will be as shown in the figure. So it is assumed in this figure that piles are flexible here. In this way, the piles can attract large lateral loads that will act in the opposite direction to the imposed displacement due to mobilization of passive pressures. Hence, due to the kinematic interaction between the soil and pile, the deformation in the piles occurs in the deeper regions as indicated in this figure. So, when we talk about the inertial interaction, the difference was that this deformation was occurring in the shallow region, but here the deeper regions will have more effect in case of kinematic loading. Now continue with that. For the kinematic loading, if kinematic loading is considered in a laterally spreading soil, in that case a more serious lateral loading condition of piles may arise when there is a non-liquefied crust situated above a liquefiable soil deposit on sloping ground, and such a condition will invariably result in what is called in lateral spreading during an earthquake event, therefore inducing large lateral displacement from the piles and pile cap. So simply what is the case here, that suppose if you have stiff soil, then soft soil. On the top of soft soil, if you have a soil layer which is a non-liquefiable, that what is called a crust, when you have a non-liquefied crust on the top of it. So that means these piles will be passing through three layers, resting on stiff soil, but first passing through the stiff crust and then coming to the liquefiable soil. And let assuming that this soft soil is liquefiable, in that case, what will happen? The top layer will exert the lateral spreading and to be considered in the analysis. So in this case, normally the non-liquefied layer that may suffer several lateral spreading may be a cohesive layer. In that case, the lateral load applied by a cohesive crust can be determined by using shallow foundation bearing capacity factors. For example, if the clay crust which is overlying the liquefied layer had an undrained shear strength denoted as SU, then the lateral pressure Q applied on a rough square pile cap in this region can simply be calculated using equation 2, which is given by Randolph and Husserl. That means Q is 3 pi plus 2 into SU. So SU is undrained shear strength of the soil. So this way one can determine this lateral pressure applied on the pile during the lateral spreading. So you could see when the lateral spreading occurs, the lateral pressure which is applied on the pile is quite large in compared to undrained shear strength of the soil as well. So this was the case when we discussed for inertial loading and kinematic loading. Now we are going to the next part, that is limit equilibrium analysis of piles under earthquake loading. So for limit equilibrium analysis, they are quite popular. Retaining walls, shallow foundations, and other geotechnical structures. It is possible to carry out limit equilibrium analysis to calculate the bending moments and shear forces in piles in laterally spreading soils. And such analysis are considered as an alternative to what is called the PY analysis. So similar to what has been done for retaining walls, shallow foundations, for this case also we can carry out the limit equilibrium analysis, and these are alternative to the load deformation curves. So let's discuss what is limit equilibrium analysis when during earthquake loading. So in this case, limit equilibrium analysis piles in laterally spreading soils. So this is the case here, figure 2.3. What is shown in this figure? The simple case of single piles in laterally spreading soils overlying a dense soil layer, and there is no non-liquefied crust above the spreading soil. So you have dense soil here. On the top of it, you have liquefiable sand, and when the liquefiable sand is there, the pile is passing through the liquefiable sand and socketed inside the dense soil. And when you have this kind of scenario, The length of the liquefiable sand is shown is here, capital L. And in this case, it is straightforward to establish a limit equilibrium model using what is called the free body diagram, which is shown in figure 2.3b. And this type of analysis was earlier presented by Dept et al. In 2003. For relatively stiff piles, the results from the limit equilibrium analysis were validated against centrifuge tests conducted in loose deposits of saturated Nevada sand with the dense sand layer simulated by lightly cemented Nevada sand. So this was, as I mentioned, this is because coming from the literature, and these are from the earlier what was work done by Dobry, Madhavushi et al., Abdon. So what is in this case? This is in figure 2.3. How this is modeled? You could see here the modeling is done. That this is the length of the liquefiable sand, and here the this on the pile, the pressure is applied, which is equal to the PL into D, where D is the diameter of the pile and PL is the pressure in the liquefiable layer. And the dense sand, because a hinge is formed here, this dense sand is replaced by a rotational spring, which is shown in this case. So free body diagram of figure 2.3 is shown in here, and continue with this using this. So let's have some formulations. Let the soil resistance per unit area offered by liquefied soil is PL. Various have estimated the value of PL to be between 8 kilopascal and 20 kilopascal, and this is based on centrifuge stress on flexible and rigid piles in laterally spreading soils, and based on shear velocity measurements were made in liquefied soil. So based on the test on the the centrifuge test, it has been observed that the value of PL may be between 8 kilopascal and 20 kilopascal for flexible and rigid piles. And these tests, further details can be found in Dobry et al. and Madhavushi. So these are some of the references. Now using this, the force applied by the liquefied soil on the pile can be calculated following equation 3. What is this equation 3? Equation 3 gives the force which is applied on the pile, and this is PL into D into L. What is PL? PL is already we have discussed, that is the soil resistance per unit area. D is the diameter of the pile. L is the length or height of the liquefiable zones. So with that we can find the force applied on this. Then the maximum bending moment which will occur at the interface with the dense soil, and its magnitude will be, so where the maximum bending moment will occur at the formation of the hinge. At this point, the maximum bending moment can be worked out using this relation half PL into DL square. Okay. Once you can find the force applied as well as bending moment. Next is, suppose if this pile cap of resting area AC is present at the top of the pile within the lateral spreading soil. If you have a pile cap, which area of the pile cap is given AC, where A subscript C, in that case the force acting on the pile will increase by the amount PL into AC, and this will lead to the additional bending moment PL into AC multiplied by L. So the maximum bending moment when you consider a pile cap on the top of it is given by relation 5. Continue with this. The rotational spring Kr is not required for estimating the maximum bending moment. However, a value of Kr is required if the lateral displacement of the pile top is required. So for calculation of displacement, Kr is required. But for calculation of maximum bending moment, the rotational spring value Kr is not required. If the lightly cemented dense sand is assumed to have a rotational stiffness of 5738 kilonewton per meter, meter in, per radian, which was quoted by Dobry et al. In 2003. If this is the case, then the lateral displacement of the pile top can be calculated using the relation 6, where the del top is the lateral displacement of the pile top, M max is the maximum bending moment, multiplied by the L length divided by Kr, where Kr is the spring constant of rotational spring. So using equation 6, one can find the lateral displacement of the pile top. It will be maximum. So this was for when the pile is passing through the lateral spreading soils. Now let's discuss the case when you have a presence of non-liquefied crust on the top of this liquefiable soil layer. And in this case, we are considering two cases. One case when stiff clay layer is there on the top of non-liquefiable layer. In the second case, when you have a dense sand layer. So let's discuss first the case when you have a stiff clay layer. So see in the figure. So the problem is here. It is similar to in the last case, but what you have now instead of two layers, you have three layers. That means on the top of liquefiable sand, you have what is called stiff clay layer. Okay, and non-liquefiable soil is at the down, and then you have liquefiable sand in between these two layers. So the points A and B where hinges are formed. So A and B, so you can say height AB, between A and B, the liquefaction of the sand occurs. Okay. So let's discuss its details. Let's consider so what you have in this case. Okay. Consider the case of a single pile of diameter D passing through a stiff clay layer of thickness H. Okay. So you have here thickness H and diameter D of the pile, and a liquefied sand layer of thickness L before entering dense sand. Dense non-liquefiable soils as shown in this figure. The soil stratification is susceptible to lateral spreading, and the stiff clay layer above the liquefiable sand will undergo lateral spreading and is capable of subjecting the pile to large lateral loads as passive soil pressures are generated. What do you have in this problem? So the top layer, which is stiff clay, is subjected to the lateral spreading, and this also applies the inertial load on the system. So for this problem, Dept et al. In 2003 describes a limit equilibrium based procedure for similar soil configuration for a relatively flexible pile passing through a lightly cemented soil layer at the top and then through a thicker layer of liquefiable sand before entering yet another layer of non-liquefiable material at the bottom, which is also made of lightly cemented sand. So this is the problem which is repeated again. So the problem is similar. The Dept et al. Problem was similar what is shown in this figure. The same procedure can be modified for the case of a stiff clay layer at the top, acting as a non-liquefiable crust. The general procedure of limit equilibrium analysis is described here. And what is the general procedure? First of all, see here, when the sloping ground suffers lateral spreading following an earthquake event, both the liquefiable layer and stiff clay layer on the top will suffer lateral spreading. So lateral spreading will occur in the stiff clay as well as liquefiable sand layer. This will cause the pile to deform as shown here, and freeboard diagram is also shown. The soil pressure and forces acting on the pile can be sketched as shown in figure 2.4b. You have here 2.4b. So what you could see, you have stiff clay, you have liquefiable sand and non-liquefiable. So in the top one, you have let's say A and B are the points between which it is expected that liquefaction of sand may occur. While about A, you have point D, which is at the top of a stiff clay layer, and point C is in between. So point C is the point where there is a change in the direction of stresses from top to bottom when you go. So the point C acts like a fulcrum where there is change in the direction. Then what you have, the horizontal forces is denoted as HA here, while moment is MA at point A. So it will happen when at the same, because you have the action and reaction, so MA and HA. Only the direction will change. Same thing for the pile tip, you have HP and MB and the direction will change. So the pile to deform, pile in this scenario, the pile will deform as shown in this figure. The deformed position of the pile is shown using the dashed lines, and freeboard diagram is shown in figure 2.4. Okay, continue with this. So then you have stiff clay as non-liquefiable layer. Continue with this, the same problem. Let's consider point A and B on the pile at the top and bottom of the liquefiable layer. Let point D be the top of the pile at a certain depth, which is ZPS, below the top of the pile, if point C is considered, and this point C demarcate a shallow region of the stiff clay layer, which applies a passive pressure from the downslope side onto the pile and the deeper region of the stiff clay. So this is shown in the figure. For the rotational spring with stiffness Kr is assumed at point B. This spring models the resistance offered by the lower layer of non-liquefiable solid to the pile. So a rotational spring is also shown here. So this is attached to. Then, assuming that the stiff clay layer above the liquefiable layer has a unit weight of gamma and unrestrained shear strength Su, consider the passive soil pressure in this layer at point D, C, and A. From point D to C, the passive pressure varies linearly from 2Su to 2Su plus gamma Z. So, which is shown in this figure. So, here between P and B and C, it is starting from 2Su. At C point, it becomes twice Su gamma. Between C and A, what is the scenario? So, the C point, the passive pressure is already given 2Su plus gamma Z. Gamma Z here. But at the base, this is further increased to S plus gamma H, where H is the height of the stiff clay layer. So this was the variation shown related to passive pressure in both the segments. Now continue with this. If suppose you have the instead of stiff clay layer on the top, if you have dense sand layer, then what is the scenario here? It is shown in this figure. You have non-liquefiable soil on the top, liquefiable sand, and then dense. So another common condition that is encountered in the field is a dense sand layer above the liquefiable layer, and this can occur in the field due to natural deposition or densification of earth prior to the construction. So this may occur because the top layer may get densified. The water table could be present at a depth of H, thereby rendering the shallow soil layer above this to be non-liquefied. So water table is at the junction where dense sand layer and liquefiable sand is there. So that means if dense sand is dry, so then chances of liquefaction decreases very much. So in this case, for this case, let's include a fixing moment, what is called M top at the pile head. So you could see M top is the moment which is the fixing moment applied at the top of the pile. This moment could arise due to resistance to rotation offered by framing action of pile group or the rotational resistance offered by the superstructure. So this was the case. Now based on this, there are some formulation when you have dense sand on non-liquefiable layer for limited analysis of piles in the presence of non-liquefied crust. For the limit state shown in the figure 2.5, the following equilibrium equations can be written assuming that full passive earth pressure coefficient Kp in the sand layer is mobilized. So for the limit state, HA can be half Kp gamma H squared D, and HB is the same thing, but the addition PL into LD, which is the contribution coming for this PL, the pressure applied to the liquefiable soils. So HA and HB you can see in this figure, okay? And HA and HA is here, while HB is the base, the liquefiable side. Similarly, MA is given from this relation half Kp gamma H cube D minus M top. M top is already defined, and MB is for the case at the point B. In that case, this is calculated from equation number 10. And in this case, M top is defined already. That is the moment at the top of the pile. So this was the case when you have dense sand as a non-liquefiable layer on the top of a liquefiable soil layer is passing through the non-liquefiable soil for dense sand. So this was all about it, and I appreciate your patience. Thank you very much, and we are done with this files.